Hi everyone. In this video I'm going to demonstrate how to perform multi-level binary logistic regression using IBM SPSS. Before we get started, let me note that underneath the video description you'll find a link to an SPSS file that I'm using in this video, so you can download it to follow along. Additionally, you will find a link to a PowerPoint that contains a lot more details that I'm going to be providing in this video. So the video itself is going to focus mainly on how to perform the analyses using SPSS, but for a deeper dive concerning interpretation, be sure to check out the PowerPoint. Now, the demonstrations in this presentation are based on an example and data by Summit and Marcelli in their 2017 article, Keep Calm and Learn Multi-Level Logistic Modeling. And this was published in the International Review of Social Psychology. So in this presentation though, I do make some changes, so it's going to alter how some of the results might appear between what I'm doing and what they do. So just kind of keep that in mind if you're following both. So let's go ahead and consider the demonstration. You can see right here I've got a screenshot of some of the data, and the authors of that article basically kind of provide a humorous example. Basically what they were doing was looking at students who were nested within schools and trying to predict the probability of a student reporting ownership of the Justin Bieber album Purpose. So the binary outcome variable is actually this Bieber variable right here, and it's coded 0 for does not own and 1 for does own. So the predictor variables, we have a level 1 predictor, which is this GPA underscore CMC variable. So this is basically student GPA centered within classrooms. And then the level 2 predictor in the models is this teacher fan variable, basically an indicator of whether the student's teacher is a fan or not of Justin Bieber. So it's coded 0 for not a fan and 1 for being a fan. Let me also note in this presentation that there is a difference in terms of the data that we're using, and that specifically is related to the teacher fan variable. So in the article that I'm referencing, they actually use an effect coded teacher fan variable, which was coded -0.5 and 0.5. So we are actually just going to stick with the original teacher fan variable, which is dummy coded in zeros and ones. So the first model that we are going to run is an intercept only model. Basically we have no predictors and we're trying to predict and essentially kind of model variation concerning the probability of owning a Justin Bieber album or that particular Justin Bieber album across classrooms. Now in logistic regression, what we do is we model the relationship between the predictors and the outcome variable, which is our probability variable, kind of indirectly through the use of logits. So probabilities, because they're bounded at 0 and 1, we have necessarily a kind of a range restriction, if you will. And what we want is a dependent variable that is not bounded at 0 and 1. So what we do is we convert or transform the probabilities into logits. So in our models, as you can see right here, you'll see that I've got my level 1 equation and level 2 equation. There's our combined equation, which is just substituting the level 2 into level 1. You'll see that the outcome in the level 1 equation is this logit ij. So that's the logit for owning the Justin Bieber album for student I in classroom J. And so again, the logit is essentially a conversion of the probability estimate. So you can see in level 1 equation we're essentially using the classroom average of the student logits as the predicted logit for each individual student. So that's what's reflected in the beta 0j that we have in that equation. The level 2 equation, what we're trying to do is model variation in the classroom average logits, and so you can see right here each classroom average logit, if you will, is equal to the grand mean of the averages plus the difference between the classroom average and the grand mean. And just to kind of provide a reminder, the intercepts in regression analysis and in multi-level analysis is essentially a mean. When there's no predictors, it's an unconditional mean. When there are predictors, then we're talking about conditional means. So as I go through this, I'm not going to use the term intercept very much. I'll probably just kind of be referring to classroom means, but that's essentially what we're capturing right here. We're essentially capturing variation in classroom means and seeing if that is significant. And the basic idea, though, in the intercept-only model is that we're trying to determine if it makes sense to utilize a multi-level modeling strategy. So essentially, one of the main reasons why we utilize multi-level modeling is to account for clustering or nestedness within the data. And so, and what that basically translates into is that there are dependents and observations on our dependent variable, and we don't want that to be occurring, because what that can do is it can yield biases in terms of our parameter estimates and standard errors, and ultimately our significance test. So what we want to do is to first determine if there is evidence of substantial clustering in the data, and if there is, then we stick with our multi-level modeling approach, and if there's not, then that might suggest utilizing a single level approach. So here we have our data opened up in SPSS. You can see that we have a pupils variable indicating basically it's a pupil identifier, our classes variable right here. We have our teacher fan variable right here, Bieber variable right here, and then our GPA CMC variable right here. So we're going to start off with our unconditional model, our intercept only model, and we're going to start off by going to Analyze Mixed Models, click on Generalized Linear, and I'm going to go ahead and reset everything. Now under Data Structure, I'm going to move the Level 2 identifier over to the Subjects box. Now before I do this, let me note that it's not going to work if we have an identifier that's set as a scale variable, like for instance this class size variable or whatever. So if this variable right here, our level 2 identifier, was set at scale, we can't move it over to the subjects box. So it's only going to work if if SPSS recognizes it as a nominal or ordinal variable. So I'm going to move this. You can see right here it's basically an ordinal variable, and I'm going to move it over to the subjects box. So it's recognizing it as a categorical variable, and that's why it can work. Under Fields and Effects, we start off with the target, and our target outcome variable is Bieber, our binary outcome right here. You'll notice that by default it sets it as multinomial logistic regression. I'm going to click on binary logistic regression right here. Then under Fixed Effects, there's not really anything to do in our intercept only model. Just note that at the bottom it's got Include Intercept, which is given right there. And then under Random Effects, we're going to click on Add Block, and under here we're going to click Include Intercept. So we're allowing those classroom means to randomly vary at level 2. So if we select off of this, it's going to say no intercept. If we select on, it's going to say intercept. Where it says subject combination, I'm going to select classes right here. So that's our level 2 identifier variable. Just so you know, there are different we have a lot of the same options concerning the level 2 variance covariance matrix that we are used to if we're running a standard linear mixed model. We're going to leave this set at variance component, click on OK, and then under Build Options, at the top up here you'll see it's got sorting order. So this is kind of important because by default it's set at ascending, and so what this is going to do is it's going to treat, for our dependent variable, it's going to treat the group that is coded 1 on our Bieber variable as the reference category or baseline category, and the group that is coded 0, it's going to be treated as essentially the comparison group. And I don't want to do that. Most of the time what we want to do is to treat our dependent variable in a way where our reference category is coded 0 and then the comparison group is coded 1, or basically the target group is coded 1. So to do that, what we're going to do is use a drop down and select descending, and so that's the sorting order for our categorical target. So now the do not own album group is going to be treated as a reference group or baseline group, and then the do own the album individuals, those will be treated as our target outcome. So that's what we want. If we had categorical predictors, we might want to do the same thing in terms of our treatments of our reference or baseline category in the target groups or comparison groups. So I'll just go ahead and select that, even though we're not going to really be using that in this demonstration. Down below, you'll see that we've got degrees of freedom. You've got several options for working with that, and then also a couple of options with respect to testing fixed effects and coefficients. So I'm just going to go ahead and leave the defaults on for these and click on Run. And so now, as we're looking at our outcome, you can see first off that there is a model summary table, and it's going to contain down here, it's got the -2 log likelihood. That is the conventional deviance statistic, and you also see that we have the Akaike's information criterion that's given and Bayesian information criterion that's given right here. Now, conventionally, these are utilized, or when when you're using maximum likelihood estimation, these can be utilized to make comparisons between different models. So these aren't useful for evaluating the overall fit of your model in and of itself. These are mainly useful when it comes to making comparisons between competing models. Now, in this particular case, though, these are basically approximations. So we're not using the standard maximum likelihood estimation approach, and so various authors have commented that this is really more tenuous to use these indices when it comes to making model comparisons. So for that reason, I'm not going to go any further in terms of talking about those. I am going to scroll down and go ahead and look under the fixed coefficients box. You can see there's our intercept. This is the grand mean of all the classroom intercepts that's given. You can see that there is a t-test and a significance value that's given. That's if you wanted to test whether the intercept is significantly different from 0. Quite often that's just not going to be very interesting or important to folks, only if there's some theoretical reason why you would want to do that. So we're not going to bother interpreting that, but we will scroll down, and you'll see that we've got our residual effect. This is basically this table right here refers to the level 1 variance. Now, in the standard multi-level modeling, where we have a continuous outcome, we would have a variance estimate at level 1 and a test of that variance estimate as well to see if it's statistically significantly different from 0. But in our case, because we're using a binary outcome variable, we don't have an estimate or significance test. What we do have right here is just a fixed coefficient. That value is fixed at 1. But we do have our variance estimate at level 2 concerning the intercept. So that down here under random effect, you can see this is the variance estimate, and you can see right here we have a z value and a p value that's given to test whether the variance of the intercepts is significantly different from 0. Just do note that the z-test that's given, or the p-value that's given for that z, is a two-tailed test, and it doesn't make a whole lot of sense to do that, because there is essentially you can't have a negative variance. But what you can do is to adjust the p-value by dividing the printed p-value in half. Doesn't really matter in this case right here because it's already significant, but sometimes in more borderline cases you might have a situation where you might want to utilize a one-tailed test. So altogether, this set of results for our random effects provides some evidence that we have significant variability in the intercepts, so which is suggesting that we have clustering going on in our data. Now, in addition to testing the variance component for our intercepts, we can also calculate an interclass correlation coefficient in order to evaluate our data for evidence of clustering. And so right here you can see that we've got the ICC. You can just simply take that variance estimate from that table I showed you just a second ago. It was a 1.133. And divide it by the sum of that variance estimate and 3.29. So you can see the ICC is 0.256, and that again is indicating that we have evidence of clustering, and really fairly substantial clustering going on in our data. Okay, so now let's proceed to a second model. In this one we're going to add in our teacher fan variable. Well, actually, for this particular case, yeah, we're going to add in our teacher fan variable at level 2 to predict variation in the intercepts, the classroom intercepts, and then we're also going to add in our GPA variable at level 1. So this is how we're going to test our question, or address our question of whether the probability of owning the purpose album varies as a function of students' GPA and also the students' teachers in terms of being a fan or not. So to carry out this analysis, we are going to go back to Analyze Mixed Models, Generalized Linear again, and we'll go under Fields and Effects, and under Fixed Effects, what I'll do is move the teacher fan variable over to the main box, and then the GPA, GMC variable under the main box as well. And at this point, there's nothing else that we want to do. We're just going to go ahead and click on Run, because we're not changing anything in terms of the random variance components. So now, looking at our output, you can see we have our box of fixed coefficients. So looking at our two predictors, you have our teacher fan variable and our GPA variable right here. So, keep in mind that the regression slopes right here, what we're doing is we are modeling predictors essentially of student logits. So that's the scale that we're working with respect to the coefficients. So you could think, formally speaking, we might say that with respect to GPA, for every 1 unit increase on GPA, there's a predicted increase of 0.672 in students' logits. And you can see that that is a pretty complex way of thinking about it. It's very counterintuitive, but it might just be easier to think about it this way, that essentially a value, a regression slope that is positive is indicating increasing probability of, in this case, owning a Justin Bieber album with increasing scores on GPA. And if that coefficient happen to be negative, that would be an indication that higher scores on GPA would be associated with lower probability of owning the Justin Bieber album. And obviously, if it's 0, that would indicate no changing probabilities across levels of the predictor variable. So at any rate, you can see right here that, again, our regression slopes for GMC and teacher fan, both of those are positive and significant right here. So that's indicating that students who were scoring higher on GPA were more likely to own the Justin Bieber album than students who were lower on GPA. And the teacher fan variable, because that coefficient is positive, that's indicating that students who were in classrooms with teachers who were fans were more likely to own the album than students in classrooms where the teacher was not a fan. When we scroll down a little bit further, looking at our random effect, you can see there's our variance component for the intercepts, and you can see it's still statistically significant. So, basically, even after we added in our predictor variables, there was still significant variation in the intercepts going on. Okay, so for our third model, what we're going to do is we're going to allow the slope for GPA to randomly vary across classrooms. So basically, there's just one minor permutation to this to our model right here. Under level 2 equations, you can see right here this beta 1j. That is what it was originally being substituted into our level 1 equation right here. And the gamma 10 is reflecting the fixed effect for GPA. So without this component right here, this would be the estimated effect of GPA on the predicted logits across all of the classrooms, and so we were treating it as fixed across all classrooms. Now in this particular case right here, because we are adding in this mu 1j, what we're doing is we're now allowing the slope, or treating the slope, as randomly varying. So now we would have a variance estimate of the randomly varying slopes as well. So to run this model, we'll go back into SPSS. We'll go back under Generalized Linear Mixed Models, and under Random Effects, I will go ahead and I'll highlight this box right here. You can see it says Edit Block. You can either double click on it or click on Edit Block. It'll open up, and then we'll move our predictor, which is GPA CMC, up to the main box right here, and that's pretty much all there is to it. Now if we wanted Right now what we'll have is a variance estimate for the intercept and a variance estimate for the slopes. If we wanted an unstructured covariance matrix, and we could easily just click on unstructured to get that. So we're just going to leave this for variance component, click on OK, and then run. And so pretty much most of our results up to this point are going to be the same, are very similar to what we had in our previous model. The only difference now, or the main difference that I wanted to draw your attention to, is that now we have the variance estimate for the intercepts and variance estimates for the slopes. And you can see that both of these are statistically significant. Now, if we want to be able to predict the variation in the slopes, what we can do is we can model a cross-level interaction. So in other words, what we would do is treat a level 2 predictor as, or include a level 2 predictor of the variation in the slopes. So to do this, we're going to make one other addition to our level 2 equation for our predictor for GPA predictor. Now what we're going to do is we're going to add in teacher fan as a predictor of the variation in slopes. And if we substitute our level 2 equations into the level 1 equation, you'll see that now we will end up with an interaction term, which is this right here. And so if that interaction term is statistically significant, then that would give an indication that the relationship between, say, GPA and the probability of owning the Justin Bieber album might vary depending on whether a student is in a classroom led by a teacher who is a fan or not. So going back into our data, we will go ahead and model this by going to Analyze, Mixed Models, Generalized Linear, go under Fixed Effects, and now we have we'll go over here to where it says Add Custom Term. So I'll click on that, and we will move our teacher fan variable to the custom term box, click on By, and then GPA CMC, move that to the custom term box as well. It doesn't matter the order, it's going to mean the same thing. We'll click on Add Term, and so now we have our interaction term that's included. So when I click on Run, you'll see that looking at our regression table, you can see that now we have an interaction, the slope for the interaction term that's given, and you can see that that's statistically significant, which would be an indication that the relationship between, say, GPA and the predicted logits, or kind of basically indirectly modeling predicted probabilities, that varies across teachers, depending on whether they are fans or not. And as you're looking at the regression output, the slope for this GPA variable right here, this would be the predicted slope for those students who are in a classroom led by a teacher who's not a Justin Bieber fan. The slope for the students in a classroom that's led by a teacher who is a fan, that predicted slope would be computed just by summing the slope for GPA, which is the 0.205, and the slope for the interaction term, which is the 0.976. Okay, so at this point I'm going to conclude this video demonstration. Like I said, be sure to check out the PowerPoint. It goes into a lot more detail. There's a lot more bells and whistles, and really a deeper dive when it comes to interpretation than I really wanted to go in this video. But hopefully this gives you a good idea about how to walk through various multi-level logistic regression models in SPSS. So thank you for watching.